these models, I'll kind of list them out, right? So believe it or not, like when I was learning about this stuff, they would teach me, here's linear regression. And then over here is logistic regression. And then over there is neural networks. And no connection was made between all of them. You know what I mean? And they're actually connected. They're almost like, if you've ever seen that cartoon of, you see like a caveman, cavewoman, right? And then you see like Renaissance and then modern person. You know how it evolves? It's almost the exact same idea, where you could literally go linear perceptron, linear regression, logistic, and so on. Got it? You're adding on to the things, and hopefully that's obvious to you. I don't know if it is, but hopefully it is. So I'll try my best to do that today, right? To convey that they're actually quite linked, and that a linear regression can be thought of as a neural network. Logistic regression can be thought of as a neural network. Perceptron is thought of as a neural network. Multi-layer perceptron all the way to deep learning. All can be thought of as neural networks. So they are, the ones that fall within this that we are discussing: perceptron, linear regression, logistic regression. Also in that chapter 4, I have a section which I call From Linear Regression to Logistic Regression. I would strongly recommend that you read through that. It has more details with a very specific example of housing prices, of how individual linear regressions can become, the logistic regression classifier. So you have perceptron, linear regression, logistic regression, MLP, which when I use the term MLP, what do I mean? I mean an input, an output, and a hidden layer in between. I always kind of mean that. And then when I mean deep learning, I kind of mean 2 hidden layers or more, okay? And then, as you know, there are advanced algorithms. So let's and we saw one of them, right? CNN. Yes, you guys, and I kind of explained that with the filter, Lena, right? We went over that, I believe. So that's CNNs. A few other advanced algorithms that we did not cover are RNNs. This is the sequential one, and of course, the transformer. Okay, these are the extremely deep pre-trained models, but they're still neural networks. They're still building on top of DL. They just have additional things going on. Okay, they're very deep. You saw like that ResNet. If you're using that for the SciFar 10 competition, I believe it has 150 convolutional layers, not just simple layers, but convolutional layers. They use something called residuals, which was not in the original code I gave you guys. Residuals actually, in my opinion, I'm finding out, is actually the thing that has made deep, really, really deep neural networks possible. And that's the scary thing of AI, right? Because they can be really deep now. And so they can do lots of things like memory possibly, and not just inference. All right, but anyway, so we got as far as here and a little bit of this intuition, but obviously we're not going to cover these 2 topics. They're just too complex. Okay, now they all come from the perceptron, and it's always good to think of them in terms of linear regression. Okay, any questions about this? Nope. All right, so this is NNs. Okay, NNs. So now we're just going to think of linear regression, right? So you guys know linear regression, right? It is like this. Okay, so you have some data, and remember that your goal is to fit a line through the data, right? That's kind of the idea. Now, one important thing is the intuition. I want to give you this intuition of how do you calculate the best line, okay? The best line. So that's kind of what I'm going to try to do as best as I can. So I'm going to do an example here, and I've got some data. The samples, and then I'm going to fit 2 lines, which I'm going to call A and B. You guys see that? So there are actually 2 lines here. So the dots are the real data, And the A and the B are what? The neural network or the function that you learn. What's important there, you learn weights, right? You learn the weights that put everything together. Okay, so once you have this, then you have X, right? This is X, and then this is, let's say Y or whatever the value is. But you say for this X, right? For this X, and I can use different colors here. So let's see. So for this X, whatever it is, X something, let's call it XI, right? The real value is this one, right? So that's real. Yes. The predicted value for the B model is this one. Do you see how what I mean by that? So this is the B predicted. So maybe I'll say real Y, BY, right? And if I keep going up, right? So this is probably like that, actually. So if I keep going up, straight line. You see that? That is AY. Yes? AY? Okay. So you see that's the intuition that we have, that we have the real value, and then we have two models. And one predicted this value, one predicted this value. So when you say the optimization of MSE, right, what are you saying? So you say something like the sum, right? So the sum divided by n of y hat minus, real squared, right? That's what we say. So what that means is, I'll use a different color here. Orange. Is that the differences here, if you look, is this is the real, right? So so the real is this value here, right? And then y here is the predicted. So it can be either y hat A or y hat B. Got it? So then what are we doing? We're taking the difference squared. Oh, that's a color that's probably not good for them. Okay, so then you've got that distance. You see that, which is the distance between the real and the predicted of B. But you also have, and I'll change to another color. Where does this one end? You see that? So it's this distance and that distance, right? So intuitively, then we can say that we have, now imagine we have many more, right? So I'll do one more. Let's say I have the real value for this one is like here, right? So then the predicted is like right there. So the distance is that one for the light blue. And then I need the distance for the dark blue, which would be what? Probably there. Yeah. Like that. Do you guys see that? So basically what we're trying to do in the minimization is what? Minimize the sum of the differences of all the points. Got it? And then the one that minimizes that gets the best, is the best weights, right? It's the closest fit. So here we could say sum of A versus the sum B, right? Where this is made up of all the differences. This is made up of all the differences. So you have, for A, D1, D2, all the way to Dn. And then here, D1B, right? D2B and DNB. You guys see that? See what I'm doing? So it's the sum of all these dark blue and the sum of all these light blue, right? And then you want the one that minimizes it. So of these, so what would the symbol be here? Which one would you expect to have a greater sum? Is it this, that, or this? Which one of these for this example? Of these three? Which one? Oh, A. Oh, you mean the first? You meant the first one? Yeah. This one, right? So then get rid of the other ones. Exactly. So you can get rid of this one. So basically, the sum of the A's is going to be greater than the sum of the B's. You see that? Intuitively, that's what this equation means, right? That, you know, you're selecting, and it makes sense, right? Because the B red line, the B straight line here is a better fit to the data. You get it intuitively? That's it. All right, so hopefully that made sense. I can't do this for every single loss, but usually this is done for MSC. We did do it for the log, right? We already went over this in the video for the log, the cross entropy. So I gave you the idea of 0 or 1 because you're trying to predict the probability. I only did it for the binary case also. Keep that in mind. Okay. Any questions about this, guys? All right, pretty easy, right? All right, so we're just going to conclude then with the comparison of all the models, and I kind of list out like the characteristics of them. So definitely learn this because this might be like on the exam. But just a comparison of what are the differences. We've gone over all of this. Okay. Here it is. All right, so we're gonna now contrast, you know, most of these at least. We've got the perceptron, linear regression, logistic regression, multi-layer perceptron, and deep learning. I'm going to skip CNNs as they are more of an advanced topic. So, but we're just going to compare these. So perceptron, right? And then linear regression. Okay, so my intention here is to show you like they're kind of the same thing, but they just, you know, have differences. Logistic regression, and also we have to draw the networks. Okay, that's the other thing. Logistic regression. MLP for multi-layer perceptron. And deep learning DL. Okay, so these are the 5, I guess, and they kind of evolve in that direction. They evolve in that direction. So we start with the perceptron. So we had in the perceptron no hidden layers, and we had a sigmoid, right? So we had something like Z equal the weights times the X values plus B. And then we had sigmoid, you remember, of Z, right? We have something like that, right? And we went over all that code in great detail, okay? If I have time towards the very end of the semester, I might do the MLP from scratch, but it's only if I get through the other topics first. Okay, so we went over definitely perceptron, and that gave us an idea of the update, right? The update of things. Then linear regression, we want to think of it. Again, we're predicting, so this predicts a sigmoid, so a type of 0 to 1, correct? So 0 to 1. Okay. Linear regression, WX plus B. What is the loss function here? Or the optimization, or whatever you want to call it, cost function. MSE, right? Mean squared error. Okay. What is the output of Linear regression. Does it predict? What's the activation in the last layer of linear regression? Does it have a function or something? What's the output? They're the same question, actually. It predicts real valued numbers, right? So you basically any value between minus infinity and infinity. Here, we constrained it to 0 and 1, right? What is the loss function of perceptron? It had that weird rule that we saw in code, remember? And we actually played with it. Don't forget. Is this clear, guys? Does this make sense? Yeah. So remember, this. What do I mean by this? This can predict 78 or age 13 or age, 23, right? That's what that means. Whereas this one can only predict 0 to 1s. How do you achieve that? Notice the difference. They're basically the same equation, aren't they? Except this is constrained by going into another function like this sigmoid that only produces 0 to 1, right? And we talked about those activation functions. Does that make sense? But whereas this one does not. Now, the perceptron goes through an activation function. Does that mean that it can approximate nonlinearities, or is it still linear? We talked about this. What is it that allows you to create nonlinearities? Not just activations. You need hidden layers. Remember, don't forget that. And it's in the GitHub, right? I provided some discussion. If you don't remember, it's in the neural nets section, I believe. Let's go over here. Get this, because I might ask this as a question. Neural nets here, right? So this was the question of question and answer of what is it that actually creates the nonlinearities? So but is just having hit now another question. What if you have 3 hidden layers but no activations? You see, you need both. That's the whole point. So perceptron gives you activations but no hidden layers. No, you can have a neural network with 3 hidden layers, but if there are no activations, it's still linear. So you need both of them, okay? But just now remember, once you have even just 1 hidden layer with activations, let's say 2, and it's a universal function approximator. In theory, it can approximate, let's say, a lot, okay? Which is what makes them what makes AI scary, because it can literally do anything. I mean, if you think about it, if it can approximate any function, that means it can deduce anything, right? All right. So anyway, so let's go back to whiteboard and wrap up. Like I said, these are more like exam questions. All right. So logistic regression. So we did this, right? MSE. Now logistic regression. This might be a tough one. So does that still look like W X plus B? And does that also look like a Z going and then Y equal C going through a function? Right? It looks like that. Now this does not update like the perceptron anymore, right? Now this will use a loss function. So now you can calculate derivatives and all of that like we just saw, gradient descent. Which one can you use? You can use cross entropy. Okay. So logistic regression, is it linear or nonlinear? Or is it a neural network? I mean, all of these are It's the way that you think about it, right? They're all the same equation, W's and X's, right? But you have to think about, does it, one way of saying this probably that's better is, does it solve problems like you want it to solve problems? Complex problems like XOR, right? We saw that only neural networks could do that. Remember that? We did the XOR. Did logistic regression solve XOR? It did not. Why? Because it's still linear. But it has an activation. So what's the problem? What does the network of logistic regression look like? If you have, let's draw it, right? So at this point, it helps to draw all these things. So let's say that we're doing iris. So logistic regression can do classification, right? This F then could be what? Any activation function, okay? So if you're doing classification, what makes sense here? For iris, let's say, just to give it a little bit more context, right? So iris is how many inputs? 4, right? How many outputs in iris? 3. So it's a classification problem, correct? Multi-class. So what activation function? So why softmax? It adds up to 1, right? So it helps out a little bit more. So that kind of makes sense here to start thinking about softmax. But do you guys see the relationship? Like, it's all kind of related, right? There's this. Now, this network, how do you draw cross entropy here? Sorry, logistic, I keep saying that. Logistic regression. What does it look like? Anything else? Or just the connections, right? So remember, so if I ask you to draw these out, believe it or not, and check the chapter 4 in the book, I drew these diagrams in there for all of these, so you can check it out if you want.
Just a question. If you use that function for...
It's essentially the perceptron, yes. Yeah, essentially. Except there is no softmax here, whereas this would have 3, this only had 1, because it was from 0 to 1. Because it's almost like you were saying, if this value was less than 0.5 or more than 0.5.
Yeah.
Yeah, that was the only thing. So this basically still gave you a value between 0 and 1, but you were just saying, like, is it less than or more than? The step function, okay, from perceptron.
Yeah.
In the output? Yeah. Maybe. You're talking about like getting like this, right? That's what you mean. If they're individual, yes, actually, because it can happen. But I think you know what, it depends on this, on the real values. If you had this, that mechanism would approximate that. Because really what you need is a machine that creates zeros or ones. Right? Do you see what I'm saying? Where if you so I would think, to answer like this, if I have a machine that produces 0 or 1 here, 0 or 1 here, 0 or 1 here, right? It can predict those. And I train it with this, like 1, 1, 0, then why not produce 1, 1, 0? It's going to learn that. Now, if I give it that, then the machinery, as it's learning the weights, it's learning to mimic it, to replicate it. So what the functions do is like this clever thing where you say, I want it to produce ones and zeros, right? And you can have multiple of them or just one. And that's why the softmax is kind of nice, because then the softmax allows you to just select one thing. It's like a little bit more pronounced in the separation. Did I answer your question?
Yes.
Yeah. All right. Yeah. Okay. Does this make sense, guys? Any other questions? But yeah, that's a good one. So yeah, so we create these models and then we use activations to kind of force what it outputs, right? Force it. All right, so we did logistic regression. We did this. Remember, we're using a loss function here, cross entropy. We kind of add this softmax idea. Okay. And these can be, so if without the softmax, what's going to happen? We can get still values, right? Between 0 and 1, right? But they just don't add up to 1. So this could end up being like 0.8. This could be end up 0.7, 0.4. They do not add up to 1, right? But that's what we can expect to get. All right, given whatever we have given it here, right? So that's literally, it learns to mimic, basically. All right, multi-layer perceptron MLP. So guys, you guys can help me out to do this one. So well, let's start with the equation. So that's WX plus B. Okay. And then how do you write the rest of an MLP here? What makes it different from the previous ones in terms of equations? This would be hidden one, right? And then that hidden one becomes what? The input to the next layer, right? So then I'm going to do, now, once I get this hidden one, now I can write this in a couple of ways, but one thing I shouldn't forget is that you need both the layers and the activation functions. Because remember, if I just draw like that, right? And then I'm going to do H2, which will be, oh, this should be 1. And I do W2, what value goes here? H1, very good, because it's the next layer, right? So that's exactly what's happening, like literally. And so this is H1B, and then I can keep stacking layers, right? So I can keep stacking layers. So I'm going to do H3, W3. Notice that the weights are different. There are neural networks where they try to share weights and stuff like that. You know, all kinds of things are tried. Now here the input is H2 because it's the previous layer. They're connecting plus B. These should be the independent Bs as well. And then the last one would be the outputs, which would be W4, let's say, H3 plus B. If I gave you this on the exam, and I ask you, is this a linear or non-linear model? Huh? You would say what? Linear, yes, a linear model. You see that? Because it's missing the activations. So, but in perceptron, we had the activation. So then you might be confused to think that it's nonlinear, but it's not, because you need, or it can't solve things with non-linearities because it needs both the hidden layers and the activation, right? And that's what I put in the blog post on the README. All right, so now what I'm missing here is the F, right? So I didn't leave much room for that. So I'm just going to do it like this. So F, F, F. These are the activation functions, right? We saw how to code this in TensorFlow. What were they? Sigmoid, tangent, ReLU, leaky ReLU, and then the softmax usually for the N if you have like a classification problem. Got it? All right. Any questions about this idea? All right, so that's a deep learning. What's the loss function for this one? Cross entropy, right? Cross entropy. And just keep in mind, and we saw this in TensorFlow itself, you select either binary cross entropy or categorical or multi-class cross entropy, right? One of those. So it's pretty easy in Keras because you literally all you have to do is just say the word. But you can write the equations if you want. Just remember, I think I've told you this before, it's just not recommended. Oh, actually, this you know, I was thinking of the deep learning. This is wrong. This should be DL. Right? Because it's got how many layers? 2 hidden layers. You guys see that? And so I made a mistake actually there. So let me just rewrite this. So this one will be the MLP, as I usually define it, or has been traditionally how I learned to define it. Very difficult to get me to change now. But so then this would be W1X plus B. So we just have 1 hidden layer, right? Start with the original X. And then here, then we can say Y equal F W2 H1 plus got it? So it just implies that there's 1 hidden layer. Okay, so if we're going to draw these in a sec, you know, just to kind of give you the last component of it, sometimes you might see the neural networks drawn, sometimes you might see it in functions, etc. And I'm trying to keep this as close as possible to the code. Any questions about this, guys? And what is the loss function of MLP? Cross entropy, once again, which is that idea of the log, right? So we went over that on Thursday. So check out the video if you don't remember. Also, it's described in great detail in the notes. So just read through it as well. Okay. All right. Yeah. So that's basically, so I'm not hearing any questions. So let's just draw the networks then, so that we have a kind of a summary. I don't have all of them here. So let's see. We have, yeah, so the original perceptron kind of looked like this. It was, I'm just going to use few neurons, ... And then we had a function from 0 to 1. That's connected, right? That's the original perceptron, linear regression. I'm just focusing on the layers here, right? That's kind of the intuition. So linear regression, how many layers? How many outputs for a linear regression? How many outputs do you have in linear regression? 1? Just 1? Could you have a linear regression of more than 1 output? Yes. All right, so that's possible actually. So you could have more, but in general, people think of linear regression as just 1 output, but there is multiple input, multiple output linear regression as well. All right. What I found about those models is that they're hard to train because one goes up, the other one goes down. It's like you maximize one error and then the other one flips. So that's my intuition with them anyway. But this is the network for linear regression. Do you guys see that? No hidden layers. Now, can you use a neural network to produce linear regression? Or is linear regression this network? What do you think? What defines linear regression is, I guess, what I'm getting at. So could I have a linear regression with 1 hidden layer? No? You did this in the homework. The Weka linear regression, do you guys remember? You could use an MLP for it. Why? Because you can a neural network can do whatever it wants, right? That's so I can have a neural network like this. Why not? And 1 or 2. What's a linear regression? Do you see what I'm saying or no? Do you guys have a doubt? What's a linear regression? Predicting, let's say that I have I'm predicting heat, right? What's the temperature here right now? Probably 70 or something. 72. Tomorrow, 75. That's a regression. You see that? That the fact that I predicted 75. What if I predict, is it gonna be hot tomorrow? Yes or no? That's classification. But a regression is just predicting a value. And I can have multiple inputs, multiple outputs, however many layers. I can use a really deep neural network. Doesn't matter. So a linear regression does not mean the network simplicity. It means that this output is a real valued number, not a class. That's linear regression. What loss function do I use if I have several hidden layers in here for a regression problem? Do I use cross entropy or MSE? Very good. Because it's just a predicted and they're real. What the network has. You guys see that? Yeah, so I'm working on a problem right now. I know this because I'm working on this problem. It's got 6 inputs, 6 outputs, where the outputs are things like, it's the Gary works, the steel works. So it's something like the steam and the heat, and you know how they produce steel, right? So you measure like how hot it is, and I don't know, stuff like that. I forget what it is. But it's 6 inputs, 6 outputs. How did we solve this? We actually did a linear model plus a nonlinear model. So it's 2 models working together, right? And so you see that's some architecture, right? You know, and well, you can try a linear model. So it's like an f that's a linear function plus another f that's a nonlinear with however many layers. What matters is the output values. Got it? Questions about that? Yeah, so any architecture can. So this kind of was like a trick question, right? But what's important is here. So all right, logistic regression. Let's see logistic. And I ask you, just draw the network for that one. So in conclusion, for linear regression, right? For regression in general. So there's actually, I should say, for regression versus linear regression, right? So for regression problem, so maybe maybe this is where I confused you guys. So I should have I should make a distinction between regression and linear regression, okay? Because nonlinear regression, okay? All right, so definitely I think I should have stressed that. All right, what about for logistic regression? What is the neural network that you guys would draw for this? For the iris data set. What else? For logistic regression? No, right? And we kind of defined that this is a linear model, correct? There could be a softmax or something, but it kind of looks like this. Okay. Questions? And let's do multi-layer perceptron. So I'm going to move over here, MLP. Yes, please. For the logistic regression, you would use something like a softmax for classification to get values between 0 and 1. Is that what you're asking?
Yeah.
Mm-hmm.
Which is
Yeah, so in a regression, and again, so I probably confused the term linear regression and just regression, right? So I want to stress really from regression, linear regression and nonlinear regression. Okay. But yeah, so your question is, in regression, is there an activation function here? There isn't. Is that your question?
In linear regression, there is no activation function.
In regression in general. In regression in general. Because linear, think of it as linear. And then non-linear, you can have a neural network in there. But logistic has an activation. Yes. That's right. Yes. Yes. So if it's a sigmoid, what are the values from 0 to 1, correct? This no just I don't know. That's the name just comes from. I see where you're. So you're thinking because it's called logistic regression that it's behaving like. That's not my fault. That's just traditionally where it comes from. Yes, that's a good question, actually. Yes, exactly right. So I think it just comes from this fact, in my opinion, that linear regression or regression, and then logistic means that you take a regression and you add this. This is sometimes called the logits, actually. You know what I mean? And so that's where that is. It's like they're saying it's almost like a regression, but it's a logistic regression because now we're constraining it to just 0 and 1. Yeah, but that's a good question, actually. This one is not meant to be an infinity to infinity. Only the actual regression one, which could be, and I should have said this more clearly, linear and nonlinear, because it could be a neural network. Questions or did you guys get confused? Or is it clear? It's clear, yeah. So that's a thing with the names, but yeah, logistic regression is basically a classification. I would say that the logistic just is that, taking a regression, but now constraining it to produce zeros and ones. Whereas in regression, whenever you talk about that, you're talking about minus infinity to infinity. Right? And as far as the architecture, then if there's like this, linear regression. So you guys were probably right that if you see linear regression, you should draw it like this. And if it says nonlinear regression, it could be a neural network. Any other questions? Clear? All right, hopefully. All right. So yeah, so what I'm trying to do, honestly, is I'm trying to like take just the original regression and put like the things, right? Put a activation, put layers, and this is how neural networks that work. If you look at CNNs, they do have a fully connected layer, but they have convolutions, they have residuals, norm. So it all starts from like this idea of regression that you start adding onto it. Okay. Questions? Nope. All right. So let's do the MLP. I think we were doing this one. Yeah. MLP. Multi-layer perceptron. This implies one hidden layer. So if you draw it, right, that's what that means. Multi-layer perceptron. And then I think I'm doing iris here. So what are the activations? So this is the input. And just imagine these are connected. Fully connected. So what are the activations here? And this is a classification problem for MLP. But if I don't put any activations here, what does that mean? It will learn to produce whatever is the real vector. So if the real vector is 2533, it is effectively a regression. Yeah? Okay. So that's what makes the regression. All right. So what's the activation here that you can use? In general, ReLU. Very good. Very good. Perfect. ReLU, right? So we've learned that ReLUs work, or leaky ReLUs. There's one called GeLU now. All right, and then this one, if it's a classification of iris, softmax, which is just make zeros and ones, but they add up to one. So it's an extension of sigmoid. Now, okay, any questions on this one? Remember that in general, they don't produce like a 0 or a 1, right? What do they produce? Like 0.005 and 0.90 or 0.98. So when you select the class, you do the argmax, right? So which basically gives you the index of the highest value in the probability. Okay. All right, let's do a deep learning algorithm. So of 3 hidden layers. So that would be an input, 1, 2, 3. Oops. For some reason, they're getting smaller. All right, so this is input, output, hidden 1, hidden 2, hidden 3. They're all fully connected. Activations here, ReLU's probably softmax if it's classification. Again, this DL, if you leave this like with nothing, it's effectively a regression. So it can learn any number that you give it. One recommendation, as always, is that you normalize the data, right? So don't forget that. All right, so yeah, so that's kind of it. I mean, hopefully I didn't confuse you there. That's it. So usually this is how I end this, just kind of showing this contrast